I was I left a lot of things unsaid, basically setting up the notion of an automorphic representation. You want me to, I was going to go over that a little bit later, more precisely, but maybe I should do it now. Any preferences? So what I'll do then, if I was going to do this later, but maybe I should just, because it's hard for people that are seeing it for the first time, that perhaps doesn't include everybody here. Lots of people here have seen it before, but nonetheless, I should define the notion of I want to describe the Hilbert space, this vector space, on which the group acts by right translation and whose decomposition gives automorphic representations by definition. So, so this is on automorphic representations, and I want to automorphic representations pi occur by definition in L2. Now I'm going to write gamma mod H for H locally compact group and actually unimodular. That means that the left and right Haar measures are the same. And gamma a discrete subgroup. Of H. Okay, I apologize if you've seen this and are familiar with it, but it's always something. I mean, historically, it was a, as I said, it was a big problem for people accepting Langlands ideas. So what are they? So what so G is, so I'm going to say well here, G is a reductive split algebraic group over Q. And I'm going to, since I do not want to go into the theory of algebraic groups, if you're not familiar with it, I will just suggest that we assume G equals GLN. Okay, so then gamma equals GQ, and that is contained as a discrete subgroup in H. So what is H? So here's the question. And the answer is that H So then that I'm just trying to set up this. So just for once and for all, trying to set it up in a way that it makes sense. So H is equal to GA equals GLNA, where A is the ring of adeles of Q. These were introduced by Chevalier. He had earlier, I think it was Chevalier that introduced them. He had earlier introduced what he called adeles, which was meant to be a slight generalization of ideals in a ring. So in any case, A is the ring of adeles of Q. Well, what is this? So that's what I wanted to say, to make it not murky, not as murky as it can sometimes seem. Well, Q, and in particular, if one hasn't seen it before, one wonders how you can write GQ as a discrete subgroup of anything. Q has, so Q is a field, and it has an absolute value on it. So it has the usual absolute value, T, and it's customary to write this as T sub infinity, because one thinks of this valuation or absolute value as an Archimedean object as opposed to a p-adic object, and so it's traditional to write infinity for the Archimedean primes. In any case, T is a rational number. So what it has the usual absolute value and its completion. R. All right, so the point is that I said this last time, but I think not sure I explained it very well. Q also, for every prime number Q, for every prime number P, has a p-adic absolute value. And the p-adic absolute value on Q reflects the divisibility of a rational number Q, which is to say that if you take a high power of P as your rational number, then its p-adic absolute value is very small. So that seems a bit perhaps counterintuitive at first, but P's are responsible for divisibility if you think of the fundamental theorem of arithmetic. So it's perhaps not surprising that you have an absolute value on the rational numbers that reflects that. And so it's absolute value, TP, for any prime P, and its corresponding completion. And the completion, once you've given yourself an absolute value on Q that is attached to P, you can do the completion operation in exactly the same way that one does it for the reals. It's completion QP, known as the p-adic field. And so let's just recall what the p-adic absolute value is. If T is a rational number, which is of the form A over B, P to the R, so this would be A and B are integers, B not equal to 0, and both relatively prime to P. AP equals BP equals 1. So you can always write a rational number like that with a power of P, R being an integer, a power of P taken outside, which is either a positive power of P or a negative power of P, and where the remaining rational quotient consists of integers that are not, neither of which are divisible by P. So you can always write a rational number like that. And then by definition, the p-adic absolute value, so it's p to the minus r. So if p is highly divisible, if t is highly divisible by p, in the sense, say, of a positive integer highly divisible by p, its p-adic absolute value is the opposite of what happens in the Archimedean case. Its p-adic absolute value is very small, p to the minus r. This would be for any t, for any rational number t in Q. Okay, so you can do the same. You check that this is an absolute value. You do the normal completion operation, which I won't go through, but you could take infinite sequence. You could take Laurent series with larger and larger in as far as the negative powers are concerned. But usual completion operation, which I guess can be done in several ways. And then, so that is the p-adic numbers. And so then the one thing one has to check is that this really is. Then the p-adic absolute value extends to this completion. Just like the ordinary absolute value extends onto the reals, and it is an honest to goodness norm. In fact, it's better than an honest to goodness norm. It satisfies the property not only is this less than or equal, not only is the sum of the absolute values less than or equal to their the absolute, not only is the absolute value of a sum less than or equal to the sum of their absolute values, but it's actually less than or equal to the maximum of T1 to the P and T2 to the P. This would be for any T1, T2 p-adic numbers. Okay, so I'll figure out this before the year's over. Well, what this means is, I mean, this is actually critical, because what this means is, that the compact subset and it's written as Z sub P, completion of the integers with respect to the p-adic values. So this would be the set of TP in QP such that the p-adic absolute value of TP is less than or equal to 1. So that's a compact subset. It's bounded and it's compact. Yes?
So what is the p-adic absolute value of 0?
0, it's 0. Yeah, I left 0 out of this business, but just like for the Archimedean place, it's 0. This is a bounded subset, compact, but the thing that makes it striking for p-adics is that it's closed under addition. So a sum of two things is closed under addition. And so that's certainly not true for the completion, the reals, the completion of the ordinary absolute value. The set of reals of absolute value less than or equal to 1 is closed under multiplication, but it's not certainly not closed under addition. But if you have this ultrametric, that's called this ultrametric inequality, this is closed also under addition. And so as a subring, it's compact subring of QP. So the p-adic numbers have some more stuff going on. And so in any case, what one does then is to put together, you've got all of these locally compact rings, infinitely many of them. So, I'm sorry, got all these locally compact fields. We put the locally compact fields consisting, so these absolute values are called valuations, as well as sometimes absolute values are just valuations. And these locally compact fields, so if I'm including the Archimedean one with the p-adic ones, perhaps it's customary to just use the subscript v. So this would be QV, where V is either the Archimedean index or a p-adic index. So we put these locally compact fields together as what is known as a restricted direct product. So I do have to say just remind ourselves what that means. That is the ring of adeles attached to Q. The point is you can do this for any number field, but Q is the easiest to describe. What it is, so it's the restricted, I'll write, it's often write P tilde or P restricted direct product of the QVs, which would be the same thing as the direct product of Q with the restricted direct product of the P's, QP's. And what is it? So I have to say what that is. This is all analysis. These are everything's supposed to be locally compact. So none of each of these fields are locally compact, but unfortunately there's infinitely many of them. And a direct product of compact sets is compact, no matter how many of them there are. A direct product of finitely many locally compact sets is locally compact, but not so for infinitely many locally compact sets. And so you do a little trick. What you do is you take the set of T, the set of TVs such that TP is a member of ZP for almost all P. So again, I have to say one further comment on this, but in any case, this is called the adele ring. Did I say that? The adele ring of Q. So let's just see if we can remind ourselves what that is. Yes, that goes up. I see. You take the second board, start off with the second board. Maybe that's better. But in any case, so thus, what this means is if S is any finite subset so any finite subset of the set of all of these valuations. So from now on, we've been using S for a finite set of p-adic numbers. We'll just expand that a little bit. The convention is to take S for being a finite set of p-adic numbers together with the Archimedean valuation. So if V is, if S is any finite subset of any finite subset of S is any finite subset of V containing, so we ask that it also contain the Archimedean valuation. And the point is we'll throw those ones out for the purpose of this construction. And AS equals the product over all V in S. Okay, so that's a finite set of indices for valuations. And so we can take the QVs there. So that's a finite product of locally compact fields. And then for the rest of them, the infinite one, we take the product over all P not in S of ZP. Okay, that is a locally compact ring. It's not a field, but it's a ring, a locally compact ring. It's not a field because we've got these components in the ring, ZP. But the point is that this infinite product, the P's not in S, is a product of compact rings, compact sets. So that's compact by Tikhonov's theorem. And this is a finite product of locally compact rings. And so that's also compact. So this product is a locally compact ring. And then, I mean, it's a purely formal construction. Okay, so then I just have to say what the adele ring is. The adele ring is then, this is a formal definition. It's, you take the direct limit over S of these locally compact rings AS. And so the adeles are then what I've said they are. I think I said it up there. The one thing that this has done is to put a little bit different topology on it. What you do is just change the topology a little bit. You take the direct limit topology and that has turned out, a direct limit topology turns out to be made to order for making this direct limit of locally compact rings still be locally compact and still locally compact. All right, so moreover, think about it for a moment. Q, this is not at all hard to check. Q sits in A because for any rational number, its p-adic absolute value, unless Q happens to be 0, unless the element here happens to be 0, its p-adic absolute value will be less than or equal to 1 for all p. So this for any given rational number. So this sits in here, and this is, I'm talking about the I'm talking about the diagonal embedding of this into here. It embeds into each of the local constituents of this. So this is the diagonal embedding. Okay, so it embeds diagonally in here and is a discrete. Now this becomes a discrete subring. Okay, so when one does, one sets this up at the beginning of a perhaps slightly more advanced algebraic number theory course, one proves these things, but these are all quite elementary things to prove. And that then is the ring of adeles. Okay, so we've got one more thing to do. Okay, since A is a ring, okay, so it's a ring, it's commutative. The usual thing that commutative algebraists always used to impose on their rings, commutative with identity. We can form, okay, so I'm leaving the case where G, if G is not the general linear group, I'm leaving that case for modest, a slight change in seeing what I'm about to write down. We can form GA. I'm thinking of G as the general linear group, just to be concrete. GL and A. So this is a locally compact group now. With embedding diagonal embedding gamma equals GQ in here, GA of gamma as a discrete subgroup. And I just have to run, there's one final thing I have to say is we have to remind ourselves what GLN of any commutative ring with identity, what it means. By definition, we know what, of course, the general linear group is over a field, but the general linear group GL and R, let's say R commutative ring with identity, this is the set of n by n matrices with entries in the ring. If it were a field, you'd ask for the determinant of x be non-zero, but if it's a ring, you ask simply that the determinant of x, you put a slightly stronger condition. You ask that it be a unit. This is the group of units in R. That way, the determinant is invertible. The element determinant in the ring is invertible. So the usual formula for the inverse of that n by n matrix, it remains an n by n matrix in this set. So that's what GLNR is. So it's defined in this way as a group. And so I guess if I can't, this is extremely confusing, all of these blackboards. Let's see if I can get this right. Maybe I pull this one down first and work on it. Would that have been recorded, me saying that the blackboards were confusing? I may have to ask him to take that out. I don't want people to think that, that I'm lost in the clouds here. All right. So I would say that I've said it, but this same construction of a group of adeles, it works. So I just say, and this is not something I'm presenting formally, but same construction. Same construction works. If G is replaced, if Q is replaced by any number field, F, and G is replaced, well, we can keep it very general. G is replaced, and one has to adjust the definitions accordingly, but G is replaced by actually any, not even a split group, any reductive group. Over F. Okay, so then in fact what we get then, we would get we would get the space GF, GAF. We could take L2 of this. We could take the regular representation R of GAF. We'll be working with the rationals, but throughout this, but the same thing works for our arbitrary number field. So GAF. I should have added some comment there. Well, I'll just say R is the regular representation of GAF on, so if I were to call this H, then G is the regular representation of GAF on H, defined by R of Y at any function phi, any square integrable function phi there is the new function whose value at x is simply phi of x, y. And phi, a member of H, a function in H. And the thing that you do need for this, you'd have to adjust it a little bit if you didn't have this thing, but the reason you take, I mean, of course, there's more serious reasons for taking it to be a reductive algebraic group, but the reason here is you take it to be a reductive algebraic group, that makes it unimodular. That means that the left Haar measure is the same as the right Haar measure, and you have to be a little careful about defining this on this Hilbert space if the left Haar measure was different from the right Haar measure. But reductive groups, that's no problem. A reductive group, I must have said this, you can talk about a simple algebraic group. It's like a simple Lie group, or it basically apart from a finite center that it might have. That's the one reason, that's the one aspect of where the notion of a simple group isn't quite right, but a simple algebraic group is one that is a simple, whose points are a simple group, apart from a possible finite center. That's a simple one. A semi-simple one is a product, finite product of simple groups, modulo perhaps some quotient of the centers of these groups. That's a semi-simple one. And a reductive algebraic group is a semi-simple algebraic group. That's a direct product with a torus. So I haven't said what a torus is, but it's basically an abelian algebraic group, but written multiplicatively. And that turns out to be a little bit different than if you write it additively. But in any case, a reductive group, so GL1 is a torus. A product of a general split torus is a finite product of groups GL1, and then you can twist the Galois action on it to have a different Galois action on this product of GL1s, and that's a general algebraic torus. I haven't defined that explicitly, but many of you will know what it is. So in any case, a reductive group is one that is a product of a semi-simple group with a direct product, group theoretic direct product of a semi-simple algebraic group times a torus, algebraic torus, possibly divided out by a finite central subgroup that embeds diagonally in those two things in the product. Okay, so that's it is, yes. If I were to talk about the Lie algebra, it's just a direct product. One tends to not talk about the Lie algebra as much for algebraic groups as one does for Lie groups, because there's a lot more stuff in the theory of algebraic groups than happens for real groups, and so the Lie algebra it still plays a role, but it's not as central to things. But yeah, you're right. Okay, so let's see, what can I do? I can push this up, and I can move this down. So, yes. Yes.
Is there any way to visualize this?
That's a good question. I don't tend to think of it that way. What people do is they tend to think, they really do tend to think of the adeles modulo Q. They're not the same at all, but they tend to think of it as Z, that the reals modulo Z. They tend to think. Because if you choose a subgroup of the subring of the adeles consisting of things which at all the p-adic places lie in the maximal compact subring, at least you're going to get something very close to this. And if you let, and so this is actually sort of an important point of how to visualize these things. If you take a bigger subring of this, consisting of things which that we don't ask that at all p-adic places they be in the subring ZP, but at say almost all of them, then you're going to get something bigger. You're going to get not Z, but let's say sort of n in Z, you're going to get some subring of Z. Maybe I'll write it as Z sub S if you ask that, if you in here choose something smaller, something larger at the p-adic places, you only ask that they be in the units almost everywhere. And as that gets, almost gets bigger and bigger and bigger, you get a bigger and bigger, you get a smaller and smaller ring there. And so this quotient gets bigger and bigger and bigger. I don't know if that makes sense, but we'll see it again. So it'd be nice, and maybe there is a way that some people think of the adeles, or the quotient of the adeles as a lattice. Yeah. Uh-huh. Yes, yes, that would be for a bigger number field. Yes. Mm-hmm. Mm-hmm. We'll see this actually in a moment. I don't know quite how far I'll get today, but we'll see this. So that actually, so I was going to do this later, but I might as well do it now because this is when we're doing the critical description of Langlands' original conjectures. So this is where we got to last time, when now where were we? So last time I defined, I gave an imprecise definition, and I'm not going to make that precise. Perhaps I should probably, I've got two sets of notes here. So let me just say that I'm repeating now the informal definition from last time, but I'll add a couple of words to it. This is the informal definition. And this is not a precise definition, an automorphic representation of. So you talk about an automorphic representation of the algebraic group without specifying the actual locally compact group that it represents. An automorphic representation of G, or, well, all right, we'll say GA. Or sometimes one writes, if you're dealing with G, this would be for G equal GLN. Sometimes one takes a subgroup of GLN, and one typically denotes it as GA1. So I'll say, so an automorphic representation of GA or GA1, the set of matrices X in GA, such that the determinant of X, absolute value, this would be the adelic absolute value, this would be the product over all V of the determinant of XV, such that that equals 1. The adeles have an absolute value on them. It's just the product of all of the absolute values in the local constituents, and that product is finite because an element in the adeles is in the ring ZP for almost all P. So those ones we're going to have absolute value 1, and so are less than or equal to 1. So you ask that the absolute value of this thing is equal to 1, and if you do that, then the reason you do this is that otherwise there is a center in GA. There's a center in GA, namely the diagonal matrices, which the group of adelic diagonal matrices which has infinite volume modulo its sorry, I don't want to confuse things by saying too much. This is, I hope this makes sense. This is a subgroup, closed subgroup of GA. This is a group that contains GQ because the product of the absolute values of a non-zero rational matrix is 1, and it's called the product formula. The product of the absolute values over all V of a rational number, a non-zero rational number, is 1. And so this is a group that contains GA, but the reason you sometimes take this group instead of this group, GQ, that GQ modulo GA1 has finite volume. If you think about it for a moment, you say, even if you're just dealing with the case of GL1, and you talk about GL1A, that would be, that's GL1A is called the adeles. GL1 is called the adeles. GL1A is called the adeles, and it contains the multiplicative group of rational numbers, and its quotient is infinite volume. So this is just a minor technical matter that one often wants to do because one wants to be dealing with an underlying space with finite invariant volume. Okay, so an automorphic representation, I've got to finish my sentence here. An automorphic representation of this group, we can just maybe keep it for that group for the moment, is an irreducible representation of GA, or GA1, if you're dealing with this other group, this slightly smaller group that occurs in the definition. In the decomposition, excuse me, of GA, decomposition of the representation R of GA, regular representation on H, the quotient. Could use either. So I'll remark on that in just a moment. But before I do so, the formal definition includes a slightly larger class of representations, which I mentioned intuitively the last time. And if you want the formal definition, there's two quite different characterizations of the formal definition. And the article that I'm about to mention of Langlands proves the equivalence of those two distinct definitions. The formal definition of automorphic representation so for the formal definition of automorphic representation, see Langlands. This was, his original article in 1969. The word automorphic representation didn't exist, and he said occurs in. He used this term. where did I write it? He actually wrote occurs in his article without making it formal. He said he wasn't making it formal. So in any case, where he made it formal was in this article on the notion of an automorphic representation. And that's in this very large and sometimes forbidding collection of articles in the Corvallis Conference from 1977 in the 2 volumes in the Symposia of Pure Mathematics from the AMS, and it's in part 1. So these are known as the Corvallis proceedings. Volume 1. So I mentioned this last time. There's a qualitative description of what it means to occur in something, and I mentioned last time that there is a part of the regular representation that decomposes discretely, the way Fourier series does, and a part of it. There are 2 parts to it, and a part of it which decomposes continuously. As a matter of fact, the continuous part is a direct sum of several continuous parts of varying continuous dimensions. And I mentioned that Langlands constructed the continuous part. His great original contribution was to explicitly construct the continuous part of the spectrum of the regular representation, modulo a knowledge of the discrete part for G, well, modulo knowledge of the discrete part for certain reductive subgroups of G. And given that, then he constructed explicitly the full continuous spectrum. But there was a question, why do I put in 1? Well, if you're dealing with GLN, if you're dealing with GLN and you write GA, there's no discrete part because there's a little bit of it that's in an infinite center, namely the diagonal matrices in the adele ring. And so if you want, I mean, it's a pretty modest, the continuous part of it is very modest, but if you want to really talk about the discrete spectrum, it's customary to throw that part away and take this. That really does have a discrete spectrum. And then that's really what the problem boils down to, because Langlands found the continuous spectrum. Okay, well, I hope that clears up a little bit about what these things mean. And next, on Wednesday, I will get into the basic conjectures, the fundamental conjectures of Langlands on these objects. Question?